Hello everybody, today we are going to discuss the lecture 1 of unit 3 of digital image processing. In this unit we are going to discuss about image degradation and restoration. I am Dr. Vibhakar Pathak from Arya College of Engineering and Information Technology, Jaipur. In this unit we are going to discuss about image degradation and restoration process, knowledge models, knowledge filters, degradation function, inverse filtering, and homomorphism in filtering or homomorphic effects in filtering. A model of image degradation and restoration process is described as a function h and a adaptive noise small n xy. The formal definition of degradation function is given by h, which is a linear position invariant process which is degraded due to some adaptive noise or some effect given by the equation in spatial domain by gx equals to hx, where hx is a function of fx plus some adaptive noise or some noise small n xy, where fx is a image which we are going to capture, gx is the degraded image, and hx is the degradation function. The model can be also described in frequency domain as guv equals huv fuv plus some noise nuv. Image restoration. Image restoration is to recover an image which has been degraded due to some unwanted parameters or unwanted events occurred in the image space. We recover this image with the help of prior knowledge of degradation phenomena, which is designed and described by the degradation function. The model of degradation is restored, or the degradation is restored by applying the inverse process in order to recover the original image, which is described in the figure. Fx is the original image which is applied, the degradation function is applied over applied over it, which is h, and the noise is mixed over that, becoming a degraded function gx, which is restored by the filter and became a new image f naught xy, which is a restored image. Fx is certainly not equals to f naught xy because the restoration can be up to 90-95% only. Noise source. To understand the degradation model, we have to understand what are the noise sources and how they are affecting the image. The noise sources are basically the noise which is coming during acquisition or transmission of the image. In image acquisition, light level, sensor temperatures, etc. are very important, as we always observe that if I am taking a photograph in which light is coming from behind the imaging body, it became darker or image is not very properly clear. It is an example of a noise or a disturbance of the image acquisition. In transmission, sometime the disturbance is due to atmospheric disturbance or the disturbance in the wire system where the data is going to be transmitted. Can be a thermal noise, it can be an isotonic noise, morphic noise, or it can be a Gaussian noise, or it can be noise like lightning, thunder, and all other type of different problems. The noise are modeled with the help of two features. One is white noise modeling and second is spatial periodic noise modeling. In white noise modeling, the Fourier spectrum of the noise is always considered to be constant, due to which we consider the zero memory based memory system of the entire space, where the noise is spreading in constant, and we can model it very easily. In the spatial periodic noise, we assume that noise is independent of a spatial coordinate. It can occur at any place and it has independent value, and they are not related with respect of image itself. Then we are talking about the types of noise. The noise are basically Gaussian noise, Rayleigh noise, Erlang noise, exponential uniform noise, and impulse noise. Here you see that we are basically having two noise in bold, which has the most effect on the degradation of the image. One is Gaussian noise, that is due to electrical noise, impulse sensor noise due to poor illumination, high temperature. This is normally taken when we are going to acquire the knowledge or acquire the image. Second is Rayleigh noise, in which we have some reflection, refraction, diffraction of the image, which cause some ranging image problem, which is also as range imaging problem, also known as Rayleigh noise. Erlang exponential noise are not available, not applicable to all type of imaging system. It is available. It is only applicable to laser imaging system. Uniform noise, it is less descriptive basis of random number generators. It is basically a noise which is white noise as per, and it got the same effect of entire image. For example, if I am taking image in a very bright light, the entire image became brighter. Impulse noise, which is quick and tangent noise, such as faulty switching, you can see in the photograph, in the the waveform, that it became impulse at different location, and it is really difficult to model, but it got some problem. That's why we can only restore up to 90 to 95% of the image. Gaussian noise is very easy to model because this PDF is given in this equation, and we all know this equation is well known to all people, that Gaussian noise, the probability distribution is very easily understand, and it has a very moderate range. If Gaussian noise is distributed randomly up to 70% of its value, its range is plus minus 1 sigma, and in 95% if it is distributed, is plus minus 2 sigma, which is very easily can be modeled and restored. Second noise which is very prominently present is called impulse or salt and pepper noise. What we have discussed, it is a bipolar noise. We have two type of probability, PA and PB, when the event Z is equals to A and Z is equals to B. Otherwise level 0 means that the impulse is present either in positive, either in negative spectrum of the imaging system in the waveform, but they are not present when there is no impulse. Means it is very linear, it is an very highly random event. Normally so it is available in a gray scale like light spot and dark spot, means it is available at the high energy level or low energy level, which we have discussed earlier. Some noise are uniform, means the noise is distributed across entire event, and it is given by probability is given 1 by B minus A. This is nothing more than average of entire your probability. Here density is given by A plus B by 2, which is basically an average, and the sigma square is given by B minus A square by 2, which is just like you are having the value of variance in the statistical model. This is the end of lecture 1. Thank you very much for the patient listening.